Next, we are going to take a look at the non-standard conditions for the redox reaction. In the previous chapter section, we already learned how to calculate the standard reaction potential or the standard cell potential, right? From using the difference of the standard reduction potential of the cathode minus the anode, which this is the known value that would be provided on a list. But in this case, this calculation that we're looking at is at standard condition. Okay, so standard state condition. For the temperature, it have to be at 25 degrees Celsius, and for the concentration, it have to be 1 molar concentration, and pressure have to be at 1 atm. Therefore, anything outside this condition would consider to be the non-standard condition. And the electrochemical potential that we are going to focus on for the non-standard condition would be without the naught sign. So for a general redox reaction would be E reaction, or if you talk about the electrochemical cell, it would represent by E subscript cell. Right? So these without the naught represent the non-standard conditions of the electrical potential. The equation that we are going to use in order to help us calculate for the cell potential at the non-standard condition is called the Nernst equation. So here is the Nernst equation. The Nernst equation is derived from here. Okay, you don't need to know how to derive it, but it's pretty much come from the fact that it's the combination between the delta G and the E cell. So according to the non-standard condition of the gift free energy and relationship with the standard condition of the gift free energy together, combined with the fact that the delta G is equal to negative NF E. So you are able to replace this term right here with the delta G part, right? Therefore, you're going to get this equation right here, rearrange it, and you are going to eventually get the Nernst equation. Okay, so these two Nernst equation will be provided for you. Okay, so one is for any temperature, the other is for at 25 degrees Celsius. So pretty much if you don't want to memorize at 25 degrees Celsius, so you can just use at any temperature, because as long as you convert this temperature to Kelvin, you would get the same answer no matter what. Okay, so pretty much these two are identical, except this one is used specifically for at 25 degrees Celsius, but this one used at any temperature. Okay, so again, I'm going to provide both equation on the cover sheet of the exam. Okay, so now let's take a look at the application of the Nernst equation. Let's take a look at example 3. Example 3 is similar to example 2 and example 1 that I show in 18.6 part 1 video. In order to determine the number of electron transfer, you will first need to make sure that the redox reaction is balanced. And in order to balance that, you will need to find the conjugate pairs between the half reactions, reduction half reaction and oxidation half reaction. And in order to do that, you will first need to determine the oxidation number of each element. For example, in this case, for nitrate ions, you assign oxygen first. Oxygen would be -2, but there are 3 of them. Total would be -6, but the overall charge of these would be -1. Therefore, nitrogen would be +5. Again, in order to calculate for this, you can set up the equation that I teach you earlier, right? So if you want to figure out nitrogen, it would be nitrogen plus 3 times 2, -2 for oxygen equal to -1. Right, set that to -1. You are going to be able to find out the oxidation number of nitrogen equal to 5. Okay, so for hydrogen would be +1, copper 0, copper +2, right? Nitrogen monoxide assign oxygen first, -2. Therefore, nitrogen would be +2. Water, hydrogen would be +1, oxygen would be -2. In this case, you see that the oxidation number of hydrogen will not change. Therefore, I would not going to worry about that. But the things that change would be, one is the copper, right? So copper going from copper 0 to copper 2 plus is indicated copper lost electrons. So therefore, this would be the oxidation half reaction. Okay. The next element that undergo change of the oxidation number is the nitrogen. Nitrogen is going from nitrogen +5 to nitrogen +2. Is indicated nitrogen receiving electron. Therefore, this half reaction would be reduction half reaction. When you know this, then all you need to do is to write out the conjugate pair between those half reactions. So I'm going to start with the reduction half reaction. Okay, so let's start with NO3 minus, right? The pair of these is becoming NO. Okay, so that's the pair of it. Another pair would be copper to plus. Okay, so you'll probably notice that I give a little bit of space because that's going to help me to balance the equations. Okay, so let's take a look at the first one, reduction half reaction. In order to balance this, first you will need to make sure the number of elements are equal. So nitrogen are equal, but the number of oxygen are not equal. Therefore, to balance the number of oxygen, you will need to add water. Okay, so I'm going to add water. So we need two more oxygen. So I'm going to add 2 more water into the reactant side, into the product side. Therefore, the number of oxygen now would equal to 3, and that's also equal to 3. That's good. But when you add water, you end up increasing the number of hydrogen. Therefore, to make the number of hydrogen equal on the reactant side, you will need to add 4 proton. Okay. Now let's see, do we need to balance this in a basic or acidic solution? This is when you would need to look at the given equation here. The given equation here doesn't have hydroxide ions, indicate that we don't have to add hydroxide to here, but you probably notice that it contains proton. Therefore, this would be balancing in acidic solution. So we can just leave as the acidic solution as in proton like that. Right. So now let's check the number of elements before we move on to the charge. So 1 nitrogen, that's good. 3 oxygen, 2 plus 1, that's 3 oxygen. 4 hydrogen, that's also 4 hydrogen, so that's good. Okay, so the next thing is make sure that the reduction half reaction has the balanced charge. Okay, so what I can do is that all you need to do is sum the charge on the reactant side and sum the charge on the product side. Okay, so the charge on the reactant side is -1 plus 4. The total would be +3. Okay, so you add the nitrate charge together with 4 of the proton. Total would be +3. Okay, do the same thing for the product. If you do it, you will see that nitrogen monoxide and water are neutral. Therefore, the charge for this would be 0. You will see that the charge on both sides are not equal. Therefore, you will need to make sure it's equal. Okay, so to balance the charge, you will need to add electron. But which sides are we going to add them? Okay, so again, reduction means it's receiving electron. Therefore, the electron should be on the reactant side. Okay, so therefore in this case, we're going to add electron. How many? Well, we have +3 here. To make it to be 0, you need to add 3 negative electrons in order to eliminate that +3. Therefore, in this case, we're going to add 3 electrons, okay, to make the charge equal. Now, let's take a look at if the charge equal yet. Okay, so I'm going to actually erase this one real quick. Okay, so now let's take a look at it. So we have 3 electrons plus 4 plus -1, right? So it's going to be -1 plus 4 plus -3. Total would be 0. Therefore, in this case, this reduction half reaction is already balanced because both number of elements and charges are balanced. Okay, so now once you finish it, go ahead, erase this part that you just used to determine it, right? So that's going to be the one. Okay, so now let's take a look at oxidation half reaction. Oxidation half reaction involves only copper to copper 2 plus. So this one is simple. So the number of elements already balanced. The next thing is to balance the charge. So the charge for this, you will need to add 2 electrons on the right hand side to make this to be neutral, the same as this, right? So now that should be balanced. Now in order to combine them, okay, so once these two are balanced, the next step is to combine them to make the overall reaction. Make sure that the number of electrons are equal. But in this case, you can't combine them yet because the number of electrons are not equal. 3 and 2, the common denominator would be 6. Therefore, you will need to make the number of electrons equal to 6 by multiply the reduction half reaction by 2. and multiply the oxidation half reaction by 3. Okay, so if you do that, you're gonna end up having 2 nitrate, okay, plus 8 proton plus 6 electron become 2 nitrogen monoxide plus 4 water. Okay, do the same thing for oxidation half reaction. So you're gonna get 3 copper become 3 copper 2 plus 6 electron. So what you're gonna do next is you will need to combine this equation here for the reduction half reaction, okay, with the oxidation half reaction that have the same number of electrons. Okay, so if you do so, you will see that the number of electrons will cancel each other out. Therefore, the overall redox reaction for this would be 2NO3 minus plus 8H plus 3 copper become 2NO plus 4 water plus 3 copper 2 ion. Okay, so when you finish, you can go ahead, write this coefficient in front of each of these species, right? So this would be 2, this would be 8, this would be 3, and then copper 2 plus would be 3, nitrogen monoxide would be 2, and water would be 4. So that would be the balance equation. If you are not sure, what you have to do, also to make it less confusing, so right now there's too many numbers, what you can do is you can erase the oxidation number that you determined earlier as well. So that way it's out of your way. Okay, so that way it would be clearer. So this would be the balanced redox reaction here. Okay, so you can also make sure as well whether your reaction is balanced or not by looking at the number of elements. Okay, and also looking at the summation of the charge. Okay, so we have 2 nitrogen, we have 6 oxygen, we have 4 plus 2, that's 6 oxygen, we have 8 hydrogen, we have 8 hydrogen, we have 3 copper, we have 3 copper. So the element is equal, okay, on both sides. But the charge, okay, let's take a look at the charge. If the charge is equal, the charge is -2 add to +8. Okay, so I'm gonna write this down. I will erase it later. So again, so this side right here, -2 add to 8. The answer of this would be 6, right? So we have +6 on the reactant side. On this side, we have 3 times +2, so equal to 6 as well. Therefore, the charge also balanced. So that means this equation is already balanced. Okay, so I'm going to go ahead and erase that. Okay, so that way we can move on to the next. All right, to the next, we see that the number of electron transfer total between the reduction and oxidation would be 6, right? So 6 electron going from oxidation and is transferred to the reduction. Copper loses 6 electron and the nitrate is accepting that 6 electron. Therefore, in this case, number of N will equal to 6 electron. Okay. Now, in order to determine the reduction standard reduction potential for each of these equations, you will need to look up the data on page 114 of the lecture manual. And here is the list of the standard reduction potential that I obtained from page 114 of the lecture manual. And if you're looking for the reduction half reaction that we determine, right, you will see that the nitrate right here, right, is matching with what we have. So I'm going to use the 0.96 volt as the standard reduction potential for the reduction half reaction. And for the copper, it's written right here. So again, we are going to not change the sign. So we are going to stick with 0.34 volt. Okay, because the following cell potential will require actually the standard reduction potential. Okay. Okay, we are going to then carry this information that we have here, including the coefficients and also the number of electrons, to the next step. And again, this is the continuous of the example 3, okay, so that we did earlier. So from the previous step, we just determined the coefficient in front of the redox reaction. Okay, so the next thing is we are going to calculate the standard reaction potential. Okay, so in this case, going to come from the value of the cathode, which is the reduction, minus the value of the anode, which is the oxidation. And the value of the standard reaction potential will come out to be 0.62 volt. Next, we are going to take a look at how to calculate the non-standard reaction potential or E subscript reaction. In this case, we will need to use the Nernst equation, and the Nernst equation is written as this one right here. Okay, so that means we already know the standard reaction potential, we know the constant, we know the temperature, we know how many electron transfer from the previous step, and this is a constant as well. Therefore, the only thing we don't know yet is the Q. So we will first need to determine the Q value of this reaction. Okay, so find out Q. Q is the reaction quotient. It's come from the concentration of the product over the reactant. In this case, it would be copper 2 plus. Okay, and then we will include gas as well, which is nitrogen monoxide. Water is liquid, we can exclude that, over the reactant, which is first concentration of nitrate ion multiplied by the proton, and copper is solid, so we can exclude that. And the last step of writing Q expression is you will need to include the coefficient as the exponent. Okay, so we have 3 coefficient for the copper 2 ion, so include that 3. For nitrogen monoxide would be 2, so raised to the power of that coefficient. Same thing for the nitrate, and same thing for the proton as well. Okay, so after you do this, then all you need to do next is plug in the value that is given, and you are going to get the value of Q equal to 3.61 times 10 to negative 15. Okay, so there are 2 significant figures here, so I'm going to just underline it so that way I don't have to round it yet. Okay, so I'm going to underline that, indicate it's going to be 2 significant figures. And the next thing that you will need to do is plug off this into the Nernst equation, which is going to equal to the E standard reduction potential that we calculate, which is 0.62 volt, okay, minus 2.303 times R, which is 8.314 joule per mole per Kelvin, okay, times temperature is have to be in Kelvin. In this case, it would be 298 Kelvin, okay, divide by the number of electron transfer, it would be 6 electron transfer, right, from the previous step that we determined. And the Faraday constant would be 69,485 joule per mole per volt. Okay, and then multiply by log of the Q value, which is 3.61 times 10 to negative 15. Okay, so and then just calculate this number out. Make sure that you cancel all the units. So let's take a look at the unit cancellation. So you will see that after you cancel joule per mole, right, that's going to be canceled out, and then Kelvin, that's canceled out. The per volt will flip up. Therefore, the final answer for the unit of this would come in volt. Okay. And the value of the non-standard reaction potential will come out to be 0.67 volt. Okay, so that would be the final answer for this. Note that because this non-standard reaction potential is asking at 25 degrees Celsius, therefore you can use another Nernst equation, another modified Nernst equation, which is equal to this equation right here, right? Plug the same value of E naught n, number of n, log Q n, and you are going to get identical answer to this one. Okay, so again, the difference between this Nernst equation and this modified Nernst equation is that this one is used for any temperature. So even if you have 25, you can use that too. But this one is only specifically for at 25 degrees Celsius. So this one can only be used at 25 degrees Celsius. So what I would like you to do is that just focus on this one, because pretty much it can be used for any temperature. So this is what you are going to use the most. Now let's try to understand the relationship between the non-standard reaction potential and the standard reaction potential. Think about this real quick. If the Q is equal to 1, which means that all of these concentration are 1, like 1 molar, 1 molar, 1 molar, 1 molar, at that condition, it would consider to be a standard condition. If you have 1 divided by 1, the Q value would be 1. Log of 1 will equal to 0. Therefore, in this case, whenever Q equal to 1 is indicate that the reaction is already at the standard condition. Next, what happens when Q is less than 1. Okay, so when Q is a lot less than 1. For example, what we see here, okay, so this indicates that Q is a lot less than 1 is telling us that at this point of the reaction contains less of the product but more of the reactant, right? Because the ratio between product over the reactant, the smaller value of the Q indicate that is have less of the product over the reactant. Therefore, in this case, because according to the Le Chatelier principle, when you have less of the product, more of the reaction is not at equilibrium yet. It's going to shift to make more of the product, to make the reaction go forward more. Therefore, it's going to be slightly more spontaneous in the forward direction to make more of the product in order to reach the equilibrium. Therefore, in this case, you will see that the E reaction at the non-standard condition would be higher than the E cell, which indicated that this reaction would be slightly more spontaneous in the forward direction than at the standard condition. On the other hand, when Q value is greater than 1, is indicated at this point is not at equilibrium yet, and at this point we have more of the product than the reactant. Therefore, in this case, according to the Le Chatelier principle, if you have high amount of the product, less amount of the reaction would shift toward making more of the reactant in order to reach the equilibrium. Therefore, in this case, if the reaction is spontaneous in the reverse direction, therefore it's going to be non-spontaneous in the forward direction. So the value of the reaction potential at the non-standard condition would come out to be less than the value of standard reaction potential. Again, to summarize this, whenever you see Q less than 1, pretty much the reaction potential at the non-standard condition would be greater than the standard reaction potential. The reason for that is because the forward reaction is slightly more spontaneous. On the other hand, when Q is greater than 1, the non-standard reaction potential will come out to be less than the standard reaction potential. The reason for that is because the forward direction becomes slightly less spontaneous. So we are going to use this concept to help us determine the relative value of the non-standard cell potential for question G, H, I, and J. Okay, so let's take a look at G. G is asking us to predict whether the non-standard cell potential would be larger or smaller than the standard reaction potential, right, at the basic pH. Okay, so what do we know is that we need to know that the basic pH contain high amount of hydroxide ions in the solution. Okay, so that's the identity of the basic solution, right? But if you're looking at our reaction here, this reaction is in acidic solution because of the presence of the proton. Therefore, in this case, as the concentration of hydroxide ions increase, this concentration of hydroxide ions would react with the available proton that present in the solution. Okay, so as these two react, it's going to neutralize each other to become water. Therefore, over time, the concentration of the proton will decrease. Okay, so that means in this case, the concentration of the proton will get will be lower. Okay, so this one will decrease. Now, if you look at the equation again, the proton is part of the reactant. So I'm going to simplify this by using reactant that undergo in equilibrium to become product. Okay, so again, as you decrease the amount of reactant, you are going to disturb the equilibrium. Therefore, the equilibrium would shift toward the reactant to make more of the reactant in order to reach the equilibrium again. Therefore, in this case, because disturbing this equation is causing the reaction to shift toward the reactant, therefore, we can say that this reaction becomes slightly less spontaneous in the forward direction or slightly more non-spontaneous in the reverse direction. Therefore, if you compare between the non-standard condition of the potential versus the standard reaction potential, you will see that because this reaction is become slightly less spontaneous in the forward direction, therefore the value of the non-standard condition would become less than at the standard condition. This is the same scenario as when Q greater than 1, which indicate that at this point of the reaction you have more of the product, therefore the reaction would shift toward the reactant, and at this point, since you have more of the product, the Q value would come out to be greater than 1. Next, what is the value of the reaction potential when the reaction reach equilibrium? Whenever the reaction reach equilibrium, the equilibrium point indicates the lowest potential of the reaction. Therefore, in this case, the reaction potential would equal to 0 volt. Okay, so this is similar to when, if you recall from chapter 17, right, when we talk about the Gibbs free energy of the reaction. At equilibrium, the Gibbs free energy equal to 0 as well. When we talk about the entropy change of the universe, when it's at equilibrium, that's also equal to 0 as well. So pretty much the equilibrium would represent the lowest potential on the diagram, right? So for example, when Q equal to K, this is at the lowest of the diagram. But when Q is less than 1, right, it's going to indicate that it's going to be spontaneous in the forward direction. When Q is greater than 1, it's spontaneous in the reverse direction. Therefore, these two are going to eventually reach at the equilibrium when the reaction would stop, because this is when all the potential energy would be at the lowest. This leads us to the next questions, right? So when Q is less than K, it indicates that this Q is not at equilibrium yet. Okay, so when Q less than K is telling us that at this point we have more of the reactant and less of the product. Therefore, in this case, at this point, the reaction would shift toward the product, right? Because you have more of the reactant than the product, so it's going to shift toward the product until the equilibrium reach again. Therefore, it's going to be spontaneous in the forward direction. Therefore, the E cell, okay, would be greater than the E naught cell, okay, because reaction shift, right? And same on the other hand, right, when Q is greater than K, is indicated at this point you have less of the reactant but you have more of the product. Therefore, the reaction would shift going from product to reactant in order to reach equilibrium again. Therefore, in this case, the E value at the non-standard condition will come out to be less than the E cell at the standard condition, which is identical to what we determined earlier, right? So pretty much in this case, it's telling us that when Q greater than K is going to shift in the reverse direction. When Q is less than K, it's going to shift in the forward direction. These two are going to shift until Q and K are equal, which is at the lowest energy, and that's when the reaction will stop, right, because it's already at equilibrium. Here is the brief summary of how to balance the redox reaction. You will need to first start with find the oxidation number for all the elements, and then determine which is the oxidation conjugate pair and which one is the reduction conjugate pair. And then you are going to split them into half reactions. You are going to write oxidation half reaction and also write out the reduction half reaction. And for each of these half reaction, then you will need to balance them. Okay, so looking at the number of element first on both side of equation, and then looking at the number of charge. Okay, so if the number of elements are not the same, what you would do is add the element to have to be the same for both sides. For example, if one side have 1 copper, the other have 2, then you just need to add 1 more copper on the other side. But for the element oxygen, when you balance the oxygen, you will need to balance it by adding water. And if you add water, the number of hydrogen will not be the same. Therefore, to balance the number of hydrogen, you are going to add the proton. Okay, so pretty much up until this step, this would be the balancing equation for acidic solution. Okay, so you can stop right here if it's basic solution, or if it is an acidic solution. But if the problem gives you a basic solution, you will need to add one more step here. Okay, so for the basic solution, after you add water and proton already, the only thing that you will need to add next to indicate basic solution is the hydroxide ions. Okay, when you add hydroxide ion, add on both sides of equation. Okay, so that way it's going to be equal, right? So how many you add on the left side, you are going to add the same thing on both sides of equation. Okay, and once the number of elements are equal, then you are going to look at the summation of the charge on both sides of equation as well. If the number of the charge are not the same, this is when you will need to add the electron. Okay, so once each of the half reaction balance, then the next thing is you will need to make sure that each of those half reaction has the same number of electron, right, for the oxidation and reduction. If they don't have the same, then you will need to multiply by a certain number in order to make the number of electron are the same. Then eventually you can combine those two and get the balanced chemical equation. Please practice more of this concept by doing the DIY problem on page 126. The key of this chapter section is already posted on Moodle. After you finish these two examples, check your answer against the key on Moodle. So since we already see everything from equilibrium to thermodynamics, spontaneity, and also electrochemistry, we are going to looking at the application of all of these by using the biological organism as an example here. First, we are going to take a look at why the deuterity is important. Let's take a look at the example of synthesis and hydrolysis of adenosine triphosphate or ATP. ATP is a molecule that carries the energy in our body. Here is the structure of ATP. It contains three groups of the phosphates and the ribose sugar and adenine base. Okay, this molecule is less stable compared to another one when it's lost one phosphate. When it's lost one phosphate, then the name would be adenosine diphosphate. That's the D stand for diamine 2, right? It's losing one phosphate group. Now it have two phosphate group, and this ATP is more stable. The more stable ATP molecule would be in a lower energy state. Okay. However, the less stable molecule of ATP would be in a higher energy state. Okay. In order for our body going from the more stable molecule or at the lower energy state to a higher energy state of ATP, our body would need to consume the energy to make the more stable molecule to become a less stable molecule. And this process is called ATP synthesis. Okay, so because we are making the ATP, right? In order to make that, the ATP will need to add another phosphate group to it. So total of the ATP would be three phosphates, for example. This process, because consume or require energy, this process is not spontaneous. This is an example of non-spontaneous process. Therefore, this process would consider to be endergonic, which indicate that the energy would be a positive. Where does the energy come from? This is where we will need to eat food, right? Because breaking down food, the catabolism will actually produce the delta G or the produce energy, and that energy can be supplied into this process. Okay, so again, the catabolism is the exergonic, which means it's going to produce energy, and the energy come from breaking down food that will supply into the ATP synthesis. Okay, so now what happened then when our body need to use energy to build up cell? This is when our body will need to break down the ATP molecule by going from the higher energy state to lower energy state. By doing this, the process would have to release the energy, and this process would be spontaneous process because would consider to be exergonic, where the delta G would be a negative value. Because this process is spontaneous, it's going to produce the amount of energy, and this amount of energy then can be used in cellular work, for example, building up cells or repairing cells. And the idea of the spontaneity help us to understand that when something is non-spontaneous, it would require energy to drive the forward reaction to occur. But when something that is spontaneous is going to produce energy. This concept also applies to the reaction potential, right? Because we know that the delta G and the reaction potential are related by negative N Fe, right? So that means in this case, when we talk about the electrical signal in our body, we can directly relate that to delta G as well, whether it's going to be spontaneous and non-spontaneous, right? Because we already learned this concept. The last thing that I would like to talk about to finish up this chapter section is why the equilibrium is dead for living systems. We know that at equilibrium, delta G would equal to 0 because at equilibrium, that's where the energy potential equal to 0. And we learned from the previous synthesis and hydrolysis of ATP, we know that in order to synthesize ATP from ADP, okay, the forward direction of this is going to be a positive delta G because it's non-spontaneous, right? In order to produce ATP. Okay, so it would require this amount of energy to produce that. But at equilibrium, because delta G is equal to 0, therefore we will not have supply of energy because delta G is equal to 0 to produce the energy storage of ATP. Therefore, our body will not be able to store the energy and therefore will not have the energy to do the cellular work, and that's going to lead to the cell death. And also, we know that at equilibrium, not only the delta G equal to 0, but the reaction potential is also equal to 0 volt as well. And the chemical reaction in our body are redox reaction, which is going to also rely on this cell potential as well. And since there is no supply of the cell potential, therefore, some of the non-spontaneous processes that happen in our body would not be able to occur. And lastly, cellular process in our body rely on a gradients of a certain ions. For example, cellular respiration is rely on the gradients of proton in order to make the reaction to either shift forward or reverse. For example, pumping the proton out of the cell versus pumping the proton in the cell. That is rely on the shifting of the reaction. But if these concentrations are at equilibrium, then there will be no movement of the ions. This would stop the chemical process in our body. Another example of biological process that involved with the Le Chatelier principle, which rely on the difference in concentration, is the respiration process. And I would use this diagram to explain that. Okay, so let's start with the chemical equation here. Hb is the hemoglobin that will react with oxygen, right, to form the hemoglobin oxygen complex. In lung, where the concentration of oxygen is high, as this concentration is high, it's going to cause the reaction to shift forward. This is going to force the hemoglobin to capture oxygen and form hemoglobin oxygen complex. And this hemoglobin oxygen complex in the red blood cell would then carry through the body to the cell to be used. In the cells where the concentration of oxygen is low, so this concentration is low, the hemoglobin oxygen complex then would be broken down in order to release the oxygen molecule to the cell and also release the hemoglobin back as well. Okay, so that means in this case, if you looking at the process of in the lung, this one would be shifting forward, right, to produce more of the hemoglobin oxygen complex. But in the cell, the hemoglobin oxygen complex will be released, which means it's going to shift in the reverse direction to release the oxygen and supply the oxygen to the cell. Okay, so what else had happened here? Well, because in the cell, according to the cellular respiration, the byproduct of this would be carbon dioxide. The concentration of the carbon dioxide in the cell would be high. Therefore, in this case, the high concentration of the carbon dioxide can also react with hemoglobin to form hemoglobin carbon dioxide complex. Okay, so therefore, in this case, as hemoglobin react with carbon dioxide, is going to form hemoglobin carbon dioxide complex. Therefore, in this case, this reaction right here would be shifting toward the product. Okay. And the hemoglobin carbon dioxide complex within the red blood cell then will be carried out to the lung again. Okay, so in lung has low concentration of carbon dioxide. Therefore, in this case, the concentration of carbon dioxide would be low. Therefore, the reaction would shift right? For the hemoglobin, carbon dioxide complex would release that to release carbon dioxide into the lung cell. Therefore, the reaction would shift toward the reactant, right? According to the Le Chatellier principle, when this is low, it's going to shift into this direction. This is how the hemoglobin releasing carbon dioxide to the lung, and then the free hemoglobin then can be used to the next circle again, and that's going to loop like this, right? So that's how we breathe. The problem is if this reaction is at equilibrium, there would be no shifting, which means that all of this concentration will be all equal. That means it's going to be at equilibrium. Therefore, there will be no shifting of the reaction. That means in this case, this whole process will not occur and we would suffocate and die. My expectation for this section is that you should be able to give me a brief summary of the importance of the spontaneity and also the equilibrium as well, and how the equilibrium affect the living system.